And we're back. What's up? How you been? What's going on? What's up? Alright, let's check out a little more GR stuff. I really do like this stuff. This gets super freaky. We saw before that electric field contributes to gravitational field. It pulls stuff in towards it. It does. It's got energy. Let's look at a similar situation, but let's get the electric field out of it. Got a mass, same as before. Now I've got a massive shell around it. Now what we're going to do is let that massive shell collapse on its own, because we don't need an electric field to speed it up as it comes inwards. The gravitational field will do that by itself. This mass right here will pull in this mass, and it will go faster and faster and faster. So we can do the same thing we did before, and then talk about what happens. Starting it off right here. We're going to test on this Gaussian surface. We're going to sit out away from all this mass. We're going to let things fall. We're going to see how hard these masses pull stuff inward. And from that, using Gauss's law like we did before, we're going to come up with a mass m1. Same mass as before, right? But now we're going to let it collapse onto itself. Right? And as it collapses, it's going to speed up, and this mass out here is going to speed up and speed up and speed up. And it's going to be going a lot faster. It's going to crash in there, and we're going to assume, like we did before, that I have some machine that's going to convert energy from its collapse into extra mass. I am going to let all that mass, all the old mass, all the new mass, pull stuff inwards, and I'm going to find a certain amount of mass, m2. Question becomes, how does m1 and m2 compare? Let me give you some options. A. m1 and m2 are equal because there was a gravitational field here that pulled the outer mass in, and it is that gravitational field that is contributing to the gravitational field out here. Gravity makes gravity. The gravitational field in here is contributing to the gravitational field out here, so m1 was already too big. And that's why they're the same. Let's go with option B. All right, let's see. Now, that's not true. We're not going to accept that. M2 is greater than M1 because all the extra mass was created. Or option C, M1 equals M2. The extra mass doesn't even register. The extra mass that we created when this thing fell on itself doesn't even register, and the two masses are the same. What do you think? Take a minute. Talk about it. The answer is M1 and M2 are equal. But not because gravity makes gravity. We can't have a theory where the source of the gravitational field is the gravitational field. It can't be a source of itself. Well, I mean, for one, how are we going to make sense of that? For two, how are we going to have a theory that would converge to anything? It's constantly making itself. It would just balloon out of it just forever. I'm not going to accept that, and I don't have to because that's not what happens. But believe it or not, the two are equal, but the extra mass from Gauss's law doesn't even register. Now you might say that you're disappointed in Gauss, or Gauss's law, because it worked before and it doesn't seem to be working now. But it's interesting that this extra mass is somehow hiding from us. mass. And Gauss's law, man, it works. You can rely on that. So, I mean, how insidious is this? How well hidden is that mass? Is it gone? Maybe it's just gone. Maybe the mass is just completely gone. Maybe if we dug a hole to the center of this thing, let's say we dug a hole, we dug around and we started counting up how much mass was inside this ball we had at the end. Started digging around through it, all right? Let's assume that in the collapse, and for the new mass that I made with my machine, the density of the mass didn't change. Let's go digging around inside and see what the volume inside is. How much mass is indicated by digging around the inside and seeing how much total volume is it. What I'm using here is the radius. What's the radius of this thing? Well, from the radius, how much volume is there? Okay, how much mass would it take to fill up that volume? We're going to call that mass to fill up that volume M3. Question is, how do you think M3 and M2 compare? M2 is equal to M3. Do you think that M2 is actually bigger than M3, or do you think that M3 is bigger than M2? Turns out that M3 is larger. There's extra mass. If you dig around inside there, there is extra mass registering. Another way of saying it is, this thing has a radius such that the volume inside is enough to hold M3, and M3 is bigger than M2. Gauss's law usually works. So, how well hidden is this extra mass from the outside? It's there. If you dig around inside, you'll come up with a volume that is enough to hold that mass. But what if we were to take our Gaussian surface, imaginary surface, and bring it down to the edge? The very edge of our new planet. The very, very edge. All right? Again, if we use Gauss's law there, it'll still register M2. Let's try something different. Let's not use Gauss's law to measure how much mass is there. Let's measure how much mass is there from the outside by looking at the surface area. Because when a ball has a certain surface area, it's got a certain volume, and we can find out how much mass there is from that. Let's say that this is surface area A3. Nice, big surface area. And we could block it off into little regions if we wanted to, like it into a globe. I am not good at drawing. All my students can tell you that. We'll put some lines here. We'll just see how many little surface areas on the edge of this thing we end up with. Right? Let's say that A3 would be the right surface area to go with R3, the big radius. Okay? Let's say that we had a different mass. Right? Let's say this is a mass that we would expect to be M3. M3 would fit in something having a surface area of that, having a volume of that. Great. All right? Consider surface area A2. I'm going to draw a lot smaller, but it's not that much smaller. But you see, you can tell. All right, and let's say from the outside, we kind of, I can't draw. It's like I don't even know what it looks like. It's supposed to look like a globe, and the lines on the globe, and whatever. We break that globe into those little boxes, and then we say, okay, from the outside, What's the surface area? Let's say this is a surface area that would contain a volume that would be right for that much mass. So, as we'd expect from geometry, this ball would have a radius r2, and that would be the right radius to go with this surface area. This ball has a larger radius, and hence you end up with a larger surface area. Question is this. We shrink this down. This extra mass has hidden from us in terms of Gauss's law. How well hidden do you think it is? Would it didn't reveal itself to us in any other way from the outside. Will it reveal itself to us from the outside by looking at the surface area? The question is this. What is the surface area of this? Is it A3 or is it A2? 1. The surface area is A3. There's nothing really hokey going on here. There's the extra mass, we went inside, there was the extra volume, everything's what it's supposed to be. If it has that volume, it has that surface area. Beach balls that have the surface area have that volume just the way it is. 2. No, actually, you think that it has a surface area too small for the larger volume. Now, I'm really saying that. I'm saying that it fooled us in Gauss's law. It's so bad that from the outside it presents itself as an object that is that big, when in fact on the inside it is that big. That would be option 2. Amazingly enough, that is how mass curves space and time. Mass actually changes. What are you doing? Mass actually changes the geometry of our world. And we end up with this one. There is too much volume inside. It really is. I mean, I don't know if it uses to build the TARDIS, but it really is like Doctor Who. As if we needed to make this any geekier. The amount of volume on the inside is too big. It's bigger from the inside than it is from the outside. It actually adds from you. We can't really blame Gauss's law. All of geometry has been fooled. From the outside, this is the smaller mass. But if you dig around, you'll find all of it somehow sitting there. So somehow, this larger radius fits in this smaller surface area. It's almost like it would have to crunch up to fit. Okay, honey, that is not helping. It's almost as if it would have to crunch up to fit. Now, don't get me wrong, it doesn't crunch up to fit. There's no wiggle in it, it's a perfectly straight line. I'm not trying to say everything's inside there, crunch up, they don't. It really fits straight. Somehow, that extra distance fits where it really should, because the mass changes the geometry of our space. For those math people out there, maybe you'd like to see it written a different way. The surface area of a sphere is 4 pi r squared, where this is the outer area, and this is the distance from the center to the edge. For this, 4 pi is different. If you want to think of it that way, this equation is done. No more, doesn't work anymore. Has to be adjusted for how much mass is inside. I hope you had fun with it. I did. I love this stuff. And you know what? I think I'm just going to keep on going and loving it. My son, Cody James! Cody chains! Here, Cody, let's do a little Caddyshack. You ready? We'll do it together with me. It's in the hole. You ready? 1, 2, 3. It's in the hole!